Welcome to this CP3 topic. We'll talk about segment trees and how to use segment trees to solve problems. So to understand the motivation of segment trees, let's start by considering range sum queries. So assuming that we have a static array that there's no update, how do we want to answer many range sum queries efficiently? So I think if you are watching this, you probably know the answer. One way to do it is to use a prefix sum arrays. So we have create another array. Each element store all the prefix sums. Then any range sum is a difference between two elements in the prefix sum array. Now the question is, can we use the similar idea to support a range max or range min queries? So prefix sum would not work. Using a prefix array would not work. Using a prefix max or prefix min array would not work because knowing the max in the prefixes, they don't give us the prefix in the they don't give us the max and min in a particular range. So they are data structures that are designed to support this range max or range min queries on static arrays. So for example, there's something called the sparse table. So the underlying idea is similar to what segment trees, but that data structure only supports the static case. So another thing that the prefix sum array doesn't support is update. So if I want range sum queries and I also want to update individual elements, so the queries and update, they may happen interactively in the sense that I may get some query and then some update and then some query and then some update and so on. So then prefix sum doesn't work because each update, you need to update the prefix sum array, which will take a linear time, so that defeats the purpose of using prefix sum. So segment tree is something that can do all of the above. So it can support efficient range queries. So here the query is not constant time, but it's a log time, which is generally good enough for many applications. And it can support many queries, not just some. It also supports max min, and in fact it supports any queries where the functions are associative. So associative means that if I want to compute the function to a set, I can compute apply the function to two of them at a time in any order. So sum definitely have that property. So addition is associative, product also associative. Max and min have that the property. So the max of 3 elements is I can first take max of this and then max with that. And there are other functions that have these properties. So long as they have associative property, then we can use a segment tree. And another nice thing that segment tree support is efficient point update. So you have an array. If you want to update any individual element, so we call that a point update, as opposed to range update when we want to update multiple elements. So segment tree combines efficient range queries with efficient point update. So that's what it does. So how to make that work? So the high-level idea for segment tree is to construct a binary tree where the leaves are the individual element in the array. So then the tree height will be log n, and the tree will have where n is the size of the array. So given the size n array, if we create a binary tree where leaves are individual elements in the array, then the height is log n. The total number of nodes in the tree is about 2n, so probably 2n minus 1. And each internal node will cover 2 to the n leaves, 2 to the k leaves, where k depends on height. So the leaves are just cover one element. Their parent will cover 2 elements, and the grandparent will cover 4 elements. And each of these internal nodes will store the pre-computed value for the whole subtree. So then if we have a range, then these can be covered using log n nodes in the tree. So this is why we can answer the range queries in log n time. That's because we only need the log n nodes to cover the whole range. So basically, when the range gets bigger, we can use nodes higher up in the tree to cover them. So essentially, at any level, so the tree has log n levels. At any level, to cover any range, we need at most two, to consider at most 2 nodes. So overall, it's a big old log n node. So let's look at this illustration from. Yeah, so suppose these are the array elements, and then we create this tree. So these are from Wikipedia. Now, if we want to cover the range, let's say starting from, let's say this S3 here. So starting from P1, ending at P7. So we need P1 to cover this. And for these two, we can use this. So this node covers these two, and this 4 nodes is covered by here, and this 4 nodes is covered by here, and these 2 nodes are covered by here. So from P1 to P7, we need P1, this node, this node, this node, and this node. So we need 1, 2, 3, 4, 5 nodes. So of course, when n is a lot bigger, then using this internal node will be saving a lot. So for any, if we look at any range query, so if we look at the individual level, it will include either 0 or 1 or 2 nodes in that level. So for this query, for this biggest query, the one we considered, then it will include at the leaf level, it will include this node. At this level, it will include this node and this node. So basically, the leftmost and the rightmost, it can include at most 2 nodes. And at this level, it includes these 2 nodes, and it doesn't include anything up there. So that's why queries can be done efficiently by using the pre-computed value. So you can view this as in some sense, generalization of prefix sum only pre-compute the prefixes. So here we are pre-computing lots of other things that are covering this blocks of power of 2, and then we can combine them to answer any queries. And if we have an update, if we want to change one of these values, for example, if we want to change this value, then we need to change this, and this. So we just need to change all the value on all the nodes along the path. So this can also be done using, this is also the log n nodes. So update can also be done in log n time. So that's the high level idea of why this works. Now let's look at so that's the first, in some sense, the clever idea is to use this binary tree to reduce the number of things you need to answer any, to cover any query, while also maintaining efficient update. The other implementation level clever idea is we actually don't need to construct a tree. We just need an array. So binary tree can be implemented using a 1D array. This is similar to the idea of a binary heap, if you are familiar with that. So there are slightly different variations, and here the code we're going to show uses this idea. So given n elements, we're going to create a size 2n array, and in particular, n doesn't need to be a power of 2 in order for this to work. So for any n elements, we just create a 2n array, and then this array is sufficient to store all the internal nodes and the leaves. And in fact, the leaves are at the end, the last n elements are corresponding with the leaves, the original arrays. Then the parent of each node will have an index I over 2. So if a node I is parent, will always be at I divided by 2. And then that also means node I's children will have will be the 2 nodes at indices 2 times I and 2 times I plus 1. So that's the how we kind of flatten this binary tree into a 1D array. Again, this is similar to binary heap. So that's the implementation idea, and we're going to look at the code next.